Okay, all right, so this is a new video stream. Today I want to talk about, it's been a while actually since I made made my live streams or the on-demand ones because I've been very busy. Hopefully this can become more of a habit. So today anyway, this is a random stream. I'm going to be talking about eBPF and specifically the entire Rust ecosystem that's being built around this technology. So let's get started actually. This is mostly, something that I would probably refer to the future me would. So just making this small video. So eBPF is a technology in the Linux kernel. It basically lets you run sandbox programs. So there's an actual VM in the Linux kernel. And you can basically inject code into the kernel space. The neat thing about this is you don't have to change the kernel source code. You don't have to load additional kernel modules, and you don't even have to change the user space side application component as well. So basically what happens with eBPF is you have your user space applications. You could go ahead and load these tiny programs called eBPF programs. They have limitations, of course. Obviously, you can't run any kind of code that you'd want. So the VM is sort of also comes with a verifier to sort of verify whether the code that you are going to be loading into the kernel is safe. It's going to look at a bunch of different things like there are no unbounded infinite loops, there's no unsafe operations that are being performed, etc. So all of that is actually verified by the kernel. But the thing about these programs are this is actually very, very useful. And people are talking about eBPF becoming what JavaScript is to the web. eBPF could probably be that to the kernel. So you could effectively write kernel code without being a kernel developer, without doing all those commits and actually waiting for it to be merged into mainline. So what can you do with the eBPF? So these are tiny, small, safe, high performance programs that run within the kernel. They have limitations, as I said, in terms of it having to be safe. They also have things like you can only have a 512 byte stack. So if you need any extra data, you actually use this thing called the maps. We'll talk about that. I'm specifically going to explore one specific map. So you can do things like monitor and control pretty much any aspect of the kernel. Network traffic, system calls, kernel events, processes, memory, a lot of stuff, everything that I've just listed down over here. You could really get down very granular to say, okay, if these conditions meet, I'd like to know, what's happening in my system. So in a way, you can think of this as runtime instrumentation of the kernel. So you can do security stuff, you can do networking stuff, you can do profiling stuff, you can do performance monitoring stuff, a lot of stuff with eBPF. And what I've actually wanted to talk about today was, so I'm going to assume this is for people who probably know eBPF, because I'm actually dealing with I'm actually learning this thing, and I'm dealing with a very specific, map that I want to work with, because I'm extracting security specific event data from the kernel, and I would like to send it somewhere. Well, I can't talk more about what we're doing, etc., but just so that I share some things that I've discovered. So without a lot more fuss, let's just get into what I'm talking about. So actually, I need to pull up. So I need So we have a tiny, example. This is pretty much ripped off the internet. It's a very basic example. What this thing does is, let me just increase the font size. What this thing does is, this is the eBPF program. It's very simple. Obviously, it's no standard, no main, and yeah, obviously everything is in Rust because that's all I do. So the program is a firewall. It's a very basic firewall. What it's trying to do is it's trying to look for a blocklisted IP address, and if it ever sees that blocklisted IP address, you're going to drop that particular packet. Now the thing about this is you don't have to at all worry about at what you don't have to figure out at what point in the packet processing pipeline do you actually deal with this. You can be as low level as possible. In fact, the thing that we're using over here is called the express data path, and you can see that it's called XDP. I don't think I'll be covering all that. I just wanted to talk about what this map thing is. So the map, as it says, it's a key value store. So there's a couple of things that happen in eBPF. Let me sort of talk about that. So if you can see over here, this myapp thing and this myapp eBPF thing. The myapp eBPF thing is the kernel component. That's the actual eBPF program that we're going to load into the kernel. And how do you do that? You actually write a user space application to load the eBPF program into the kernel. Now, these two things are different. So one's running in the kernel, the other one's a user space application. You want to actually extract security event data from the kernel and then make that available to user space. So eBPF actually hooks into Linux's other subsystems, specifically what's called the perf subsystem. Perf, is a very big subsystem. It basically is for performance monitoring. But what we can also do is the event that we've captured, so for example, if this particular eBPF program runs, which is try XDP-firewall is the program, if it runs, it's going to look at the blocklisted IP address. It's going to capture information about what action it took, and it's going to sort of output that somewhere. And that outputting is basically, it's going to output it to a certain buffer in kernel space itself. And then we get to read that in user space. And I'll sort of talk about that. So that particular, that whole process, the IPC process, uses the perf subsystem. Now the way it actually works is, let me see if I can show you some diagrams that I've sort of put together. Hopefully this should make sense. So the first thing is, from user space, you actually do what's called a load. You try to load the eBPF program. Before you load it, all the maps that we've declared in the eBPF program, we attempt to initialize it and then create the map. So we create the map in the user space kernel. Now each element of the map is a key value pair. So the keys are nothing but CPU IDs, the numeric IDs of any CPU that's currently online. The keys are the numerical IDs for that, and the values are pointing to the file descriptors of the target buffer. It's essentially the place where the kernel component is outputting. We're trying to get that FD or the file descriptor to that, and it sort of looks something like this. So you get the FDs, it points to the output buffer. Now each output buffer is sort of a per CPU buffer. That's one thing about that's about the perf subsystem. It's a per CPU circular buffer that is only accessible by every individual CPU core. They don't actually share it. Now there's another version of this that's come out. It's called the ring buff. That's shared. It does this multiple producer single consumer thing, which I don't want to get into, but this is going to be quick. So effectively what happens is, let's actually just sort of walk through this. So here in main, we have a BPF structure. This is like the main core entry point for the Rust eBPF library called Aya. If you actually if you actually go into this, figure out how the load, what it does when it's actually loading the eBPF bytecode, it does a bunch of different things. It actually loads the eBPF bytecode, and at the same time, I've actually looked at a couple of things. It also creates the map here, which is essentially what I just showed you. It creates the map through a system call, and once it creates the map, it gets an FD back. Now that file descriptor, interestingly, is also what you call patched in to the actual bytecode. So you get the file descriptor for the map that you just created in kernel space, then you patch it into the bytecode, and that is what you load, that's the program that you load, and line number 48, that's what you load into the kernel actually. All right, so this load prepares, sets up something, does a couple of initialization things, and then it loads it into the kernel. Then the next step is what happens here. You see that apart from all the system calls, the BPF system calls that I just talked about, creating the map, updating the map, all of that, the file descriptors that actually point to the target buffer into which events are going to be written into. How do you get that? As I said, there's the perf subsystem. You just call perf event open. You get that file descriptor back. You use that file descriptor in user space to create, basically memory map whatever kernel space that you're referring to into user space, so that you don't have to do any kind of memory copies or context switches. So effectively, you only get it once, and it's very fast. And then finally, you hook up your eBPF program to the event, to the attach point, and you're done. And as you can see, I'll walk through all of this, because this is going to look alien if you're not walked through this. So we've loaded the program over here. We basically pulled a map, the map that we were talking about, and we're trying to, we call this open method on the app. And if you can see, the CPU IDs of all the CPUs that are online is what we're looking at. If you basically go into open, you'd see that, I just want to get to the point where you actually do the final open, because there's multiple levels of indirection, because there's a lot of types in between, not important. So here's where you call the actual perf event open. You're actually you're calling into the kernel's system, you're doing a system call, you get your FD, then you do your memory map, as I said, and then depending on whether that's passed or failed, you can return an error. Lastly, you can also do the hooking up using another system call called IOCTL, and that's what you return. Now, when you do return, you see you actually update the the map that you've created originally before loading your eBPF bytecode. You update that. So from the kernel, this happens in the user space, and in the kernel space, what happens is, because we've already sort of embedded the file descriptor to the map, and we know that each key in the map is actually a CPU ID, we'll just go ahead and output it, output events to whichever CPU this particular eBPF program is running on, and user space can pick it up and read it from there. All right, so yeah, there's a whole bunch of concepts which I have not clearly explained. This is, again, just me trying to put my thoughts together. In case you have questions, etc., if somebody else is watching this, just leave a comment. I'll be able to get back to you with a better answer if you're working on this. All right, so yeah, just that today. And yeah, so I guess that's about it. So this was interesting to see that, A, you create this map, B, you try and do this, kernel to user space communication, or IPC, or whatever you call it, using this perf subsystem. Obviously, the perf subsystem is not so great because there's copying going on, and also the events that you collect from the kernel may not be in order. And as I said, there's another map type that was maybe added to the Linux kernel. That's eBPF. About a year or 2 years ago, it's called the ring buffer. And that's more, that's probably a replacement for this. You don't have the extra memory usage. You don't do the copies. You don't have to worry about ordering as well, because that particular map type is backed by an MPSC, a multiple producer, single consumer queue. So you can have multiple cores actually producing events, and then you can have a single consumer at the other end, sort of consuming those events. And it's also implemented well in the sense that, you could simultaneously, sort of produce, or rather reserve some space in the buffer and then commit your writes, etc. There's a lot of stuff, we don't need to get into that. But yeah, so that's eBPF, and that's a quick stream. Hopefully I did that. Okay, let me stop.